Welcome to the floor of the Bot Lab. Meet Bolt, our lead assembly robot. Bolt claims the primary line is perfectly calibrated to output metal brackets with a mean weight of exactly 50 grams. But QA robot Nut isn't going to just take Bolt's word for it. To verify Bolt's claim, Nut uses a formal statistical process. As this slide outlines, we begin with Step 1, define the question and formulate a hypothesis. Then, Step 2, choose the appropriate test statistic based on the distribution of our data. Moving to the next slide, we complete the procedure. Step 3 is establishing the test criterion, setting up a critical value and region. Finally, Step 4 requires us to draw a conclusion, deciding whether to accept or reject our hypothesis. Let's apply Step 1 to Bolt's assembly line. Looking at the third option on this slide, Nut sets up a two-tailed test. The null hypothesis is that the mean bracket weight is exactly 50 grams. The alternative hypothesis is that the mean is not equal to 50 grams. It could be heavier or it could be lighter. Next, we establish the test criterion. Think of the critical value as physical tolerance limits, represented by glowing calibers. We drop our test statistic bracket onto the scale. It's too heavy, landing in the red rejection region. We reject the null hypothesis. Bolt starts panicking, claiming this might just be a false alarm. That brings us to this decision table. Bolt is worried about a type 1 error, a false positive, halting a perfectly fine machine. Nut worries about a type 2 error, a false negative, shipping defective brackets to customers. Testing the population mean is our first line of defense. It ensures the average output meets our strict specifications, keeping the entire assembly process anchored and preventing systemic drift over time. Bolt recalibrates the machine. The average weight hits exactly 50 grams, but the machine is shaking violently. Looking at the distribution curve of the bracket weights, the peak is dead center, but the curve is wide and flat. We are getting a chaotic mix of paper-thin parts and heavy, chunky brackets. To address this instability, we test the population variance using a chi-square distribution. Unlike the mean, where we cared about both too heavy and too light, here we only care if the variance exceeds a maximum safe threshold. That makes this a one-tailed test, concentrating our entire rejection region on the far right side. Let's test your intuition. Pause the video for a second. Based on this physical logic, how would you write the null and alternative hypotheses for this specific right-sided test? Here is the setup. The null hypothesis states the variance equals our acceptable baseline. The alternative hypothesis, the problem we are trying to catch, is that the variance is strictly greater than our baseline. We calculate the variance test statistic. If we visualize our data as orange liquid filling a pressure gauge, the pressure surges past the strict red marker of our critical value. We are deep in the rejection region. This shows exactly why variance testing is critical. You can have a perfectly accurate mean, but if your variance is too high, the machine is still producing entirely unusable parts. Now we move to a different line in the lab, sorting boxed microchips. We are no longer measuring physical weight, we are measuring pass-fail categorical data. As this slide shows, we use hypothesis tests for proportion. Bolt claims the defect weight is under 2%. The null hypothesis is 0.02. The alternative is greater than 0.02. The sample tally crosses 30, providing a valid dataset. The test statistic dial lands safely in the green zone. We do not reject the null hypothesis. By getting this right, Nut avoids a massive type 2 error. If the test statistic had been wrong, the factory would have accepted a bad batch of microchips and sent defective hardware out the door. Mastering quality control requires knowing which tool to pull from your kit. Use the two-sided calipers to check if your population mean is drifting. Use the pressure gauge to test if your variance is shaking out of control. And use the sorting bin to check the proportion of defects in large samples.